A quick review of thermochemistry. The first law of thermodynamics. And let's put a big underline under this. Basically, it's another statement of the conservation of energy. Energy cannot be created or destroyed. Another way of saying this is, the energy of the universe is a constant. Although the energy of the universe is constant, you can have many different forms. Okay, so for example, in molecules, you have potential energy that is stored in the chemical bonds. Again, atoms and molecules can have kinetic energy when they're moving about. And over here, this is acetylene, and the bonds are shown by these horizontal lines. Let's take a reaction that illustrates the first law of thermodynamics. We're going to burn acetylene in oxygen and come up with carbon dioxide, water, and energy. So you're going to say, where is that energy coming from? Well, what's happening is the bond potential energy is being lowered. Energy released by the system is converted to thermal energy in the form of kinetic energy that heats the surroundings so other particles start moving more quickly. So energy has changed form, but the total amount of energy remains constant. So you had the potential energy over here turning into kinetic energy over here. Now those of you who know about Einstein and E equals mc squared will hopefully now say, but wait a minute, sometimes you create energy out of matter. And that's true, but now you're into the nuclear physics part of the thing where you're breaking apart nuclei. We're just dealing with electrons here. We're not really converting any mass to energy, so energy will remain constant. So if you look at this picture on the right here, you have your acetylene up here at a certain amount of internal energy up here. You add oxygen to it, burn it, and you go down. Your internal energy decreases. So down here, the carbon dioxide and water, you have less internal energy, but more kinetic energy. Another way of looking at the first law of thermodynamics is this equation right here, where the change in internal energy is equal to the work done either on the system or by the system, and the heat transferred either into the system or by the system. Energy cannot be created or destroyed. The total energy of the universe is a constant. So if we apply it to a process like we did on the previous slide, we show that total energy is conserved, but it does change forms. So for this first illustration on the left, we have the potential energy of the system decreasing and kinetic energy of the surroundings increasing. That was burning acetylene and oxygen. So you can imagine it goes the other way. You can gain energy from the surroundings, which will increase your potential energy of the system, and the surroundings' kinetic energy will decrease. If you're not quite convinced about the systems and surroundings definition, go back to the previous unit where it was defined in quite a bit of detail. But let's draw a little picture here. We isolate a small part of the universe, and we call that our system, and we want to see what happens to it. Everybody else in the universe is called the surroundings. And here we go. We have C2H2 plus oxygen yields carbon dioxide plus water and energy. The system is the reactants and the products. The surroundings is everything else around the system. So for a reaction, which is what this is up here, the first law of thermodynamics deals only with how much energy is involved in the change. Does energy flow in or out of the system? Does energy flow in or out of the surroundings? And what form does the energy take? Is it heat? Okay, heat is Q. Or is it work? Or is it an increase in the potential energy? Another name for that is your internal energy. The first law of thermodynamics, or the conservation of energy, is an incredibly powerful tool. However, it is limited. Let's show how that happens. We have sodium reacting with water to form sodium hydroxide and hydrogen gas. Okay, let's flip it around. What if we add sodium hydroxide plus hydrogen? Can that form sodium and water? So does the reaction go in that direction or in that direction? We don't know. Well, we do know, but the first law of thermodynamics won't tell you. Given those equations, we cannot answer that very simple question, which way does the reaction go? So we're going to spend some time now determining the direction of a reaction.